The generative AI revolution. Imagine you're an archaeologist who has just discovered a chamber full of mysterious artifacts with no labels or instructions. Your task is threefold: group them by style, identify the fakes, and imagine what missing pieces might have looked like. This is the essence of unsupervised learning. But when you can create entirely new artifacts that look authentic, you've entered the realm of generative modeling. Today we'll explore the three pillars of modern generative AI, not through equations alone, but through visual intuition, real examples, and the architectures that power tools like DALL-E and Midjourney. These technologies are reshaping how we create, understand, and interact with data. Let's begin. Section 1. Autoencoders, the data compression pipeline. An autoencoder is fundamentally a data compression pipeline that learns on its own. Think of it as a sandwich: two neural networks with a tiny bottleneck in the middle. The encoder squishes your image into a compact code, a latent vector, while the decoder rebuilds the original from this tiny summary. This forces the network to learn what's truly essential about your data. The loss function is brutally simple: pixel by pixel difference, which we call reconstruction loss. It's like making notes of a movie and then retelling it from memory. The better your notes, the closer your story matches the original. Visualizing the latent space. When we force the bottleneck to just 2 dimensions, we can actually visualize how the network organizes reality. Thousands of missed digits scatter across a 2D plane, naturally clustering by similarity. Similar digits live close together. This is dimensionality reduction that captures nonlinear relationships far better than PCA. The structure reveals the network's understanding. Zeros and ones form tight groups on one side, while sevens, eights, and nines flow smoothly on another. The digits 2, 3, and 4 create a gradient in between. This organization emerges without explicit instruction. The network learns it purely from the reconstruction objective. Autoencoder applications. Autoencoders extend far beyond simple compression. Feed them noisy images, and they learn to ignore the noise. The reconstruction loss naturally penalizes noise while preserving essential features. Feed them anomalies like a cat in a digit dataset, and the reconstruction error spikes dramatically, screaming, "This doesn't belong." This makes autoencoders powerful for anomaly detection in manufacturing, healthcare, and cybersecurity. The third major application is data compression. Large files shrink to tiny latent representations, then expand back with minimal information loss. Section 2. Variational autoencoders, making latent space continuous. Regular autoencoders have a fatal flaw. Their latent space has gaps. Sample a random point in these gaps, and you get digital soup, meaningless noise. The VAE fixes this by making the latent space smooth and continuous. Instead of learning a fixed point for each input, the encoder learns a distribution, a cloud of possibilities. The encoder outputs 2 vectors, a mean and standard deviation. Every image becomes a fuzzy cloud in latent space. But here's the problem. Sampling is random, and randomness breaks backpropagation. Gradients can't flow through stochastic nodes. The reparameterization trick. The reparameterization trick is the cleverest hack in deep learning. Instead of sampling directly from the distribution, which breaks gradients, we make randomness external. We sample external noise epsilon from a standard normal distribution, then combine it with mean and standard deviation using simple arithmetic, z equals mean plus standard deviation times epsilon. Now sampling looks like multiplication and addition, fully differentiable operations. The gradient flows unblocked through deterministic nodes. The randomness is still there, but it's decoupled from the learned parameters, allowing backpropagation to work perfectly. Beautiful, isn't it? Weight loss function and applications. The VAE has 2 competing goals in its loss function, represented as a balanced scale. The first is reconstruction, keeping the output accurate, measured by MSE. The second is a KL divergence term that acts as a regularizer, forcing the learned distribution to stay close to a standard normal distribution. This KL term prevents the encoder from creating arbitrary distributions scattered throughout latent space. Instead, all clouds overlap with the standard normal, creating a continuous, navigable latent space. The result is disentangled representations where each dimension controls one factor of variation. The demonstration shows latent space arithmetic: z king minus z man plus z woman equals z queen. Faces morph smoothly through the latent space. Moving one slider changes only the digit's thickness, another changes rotation. This interpretability is unique to VAEs. The VAE is creative, but it's a bit blurry. For photorealism, we need competition. Section 3. GANs, the adversarial game. Welcome to the most dramatic concept in deep learning, generative adversarial networks. A GAN is a two-player game where the generator is a forger and the discriminator is a detective. They train by trying to destroy each other. The generator takes random noise and outputs a fake image. The discriminator takes both real and fake images and outputs scores indicating whether each is real or fake. The generator tries to create fakes that fool the discriminator. The discriminator tries to catch them. This is minimax optimization, a mathematical arms race. The genius of this approach is that when the detective can no longer tell real from fake, the forger has learned to generate perfect data. But achieving this balance is razor thin. Too much pressure from either side breaks the training process. Training dynamics and mode collapse. Training GANs is notoriously unstable. If the discriminator becomes too good, like a teacher who always catches cheaters, the generator gets no gradient signal and stops learning. This is training instability, and it's one of the primary challenges in GAN development. Even worse is mode collapse. The generator finds a few perfect fakes that fool the discriminator, then stops exploring. It forgets the rest of reality exists. Instead of generating diverse outputs, it produces the same few high-quality samples repeatedly. Researchers have developed several solutions to these problems. Gradient penalty prevents the discriminator from becoming too sharp. Spectral normalization stabilizes layer weights. Two timescale updates give the discriminator and generator different learning rates. GAN evolution. The GAN family tree shows remarkable evolution. DC GAN gave us the first architectural rules for stability, batch normalization, strided convolutions, and no fully connected layers. It was our first reliable image generator, proving that GANs could produce coherent 64 by 64 images. CycleGAN mastered translation without paired examples. It transforms horses to zebras, summer to winter, Monet paintings to photographs, all without seeing examples of the transformation. It uses cycle consistency. Translate forward, then back, and you should return to the start. This clever constraint forces the model to learn meaningful transformations. StyleGAN represents the photorealism champion. It separates content from style by using a mapping network that reshapes noise into a disentangled latent code, then injects style at every layer. This enables independent control over hair, age, pose, and other attributes. Section 4. Diffusion models, reversing noise. Imagine taking a pristine image and adding noise over 1,000 steps until it's pure static. Now, train a neural network to reverse that process. That's diffusion. The forward process is fixed, just add Gaussian noise at each step. The magic is learning the reverse. At each step, predict what noise was added, then remove it. Instead of generating in one shot like a GAN, diffusion iteratively refines. It's slow, hundreds of steps, but remarkably stable. The loss is simple MSE. There's no adversarial game, no discriminator, no minimax optimization. Just a straightforward prediction task. Given a noisy image and a time step, predict the noise. This simplicity is revolutionary. Diffusion models have proven more stable to train than GANs and produce higher quality results than VAEs. Training and sampling process. The training loop is elegantly simple. Take a clean image, pick a random time step, add noise to the image according to the forward process. Train the model to predict that noise. That's it. The model learns to denoise at every time step, building up a complete understanding of the reverse process. For sampling, start with pure static. Run the model repeatedly, each time removing a bit of predicted noise. After 1,000 steps, you have a perfect image. The model has learned to sculpt reality from chaos step by step. This iterative process is the key to diffusion's stability and quality. Each step is a small, manageable prediction task. The model learns to gradually refine the image, removing one layer of noise at a time. Stable diffusion, the practical hybrid. Full diffusion on large images is computationally brutal. A 512 by 512 image has 262,144 pixels. Running 1,000 diffusion steps on this would require enormous computation. Stable diffusion's genius is doing diffusion in latent space instead. The process is elegant. First, a VAE compresses the image to a tiny 64 by 64 by 4 latent representation, a 256-fold reduction in dimensionality. Then, diffusion operates in this tiny latent space, which is far more efficient. Finally, the VAE decoder expands the refined latent back to a full 512 by 512 image. This hybrid approach combines the best of both worlds, the stability and quality of diffusion with the computational efficiency of VAE compression. It's why DALL-E 2 and Midjourney are both fast and stunning. Model comparison and pro tips. Let's summarize the four major generative approaches. Autoencoders are stable and excellent for compression and anomaly detection, but they're not truly generative. They can only reconstruct variations of training data. VAEs offer a smooth, latent space and creative capabilities, but outputs tend to be blurry due to the averaging effect of the reconstruction loss. GANs are fast and produce photorealistic images, but training is notoriously difficult and unstable. Diffusion models achieve the highest quality and most stable training, but sampling is slow due to the iterative refinement process. Each model has a character. The autoencoder is an analyst with a magnifying glass, understanding data structure. The VAE is an artist with a palette, creating with interpretable control. The GAN is a forger with a mask, competing to fool others. The diffusion model is a sculptor with a chisel, carefully refining from chaos. My pro tips? Start with autoencoders to understand your data structure. Use VAEs when you need interpretable, disentangled control. Choose GANs when speed is critical and you have resources for careful tuning. Pick diffusion when quality is paramount and computational cost is acceptable. And remember, the future is hybrid, as stable diffusion proves. Conclusion. The generative trinity. These aren't competing technologies. They're complementary tools in your generative AI toolkit. The autoencoder understands your data. The VAE interprets it with creative control. The GAN competes to produce photorealism. The diffusion model sculpts the highest quality results. Master them all, and you hold the keys to creating reality itself. The best model isn't the shiniest. It's the one that fits your data, your computational resources, and your mission. A startup with limited compute might choose VAEs or GANs. A research lab with unlimited resources might prioritize diffusion for quality. A production system might use autoencoders for anomaly detection and diffusion for generation. The field is evolving rapidly. New architectures combine elements of all four approaches. Transformers are being integrated into diffusion models. Hybrid systems leverage the strengths of multiple approaches. The future belongs to those who understand these foundational concepts and can adapt them creatively. Now, go forth and generate, but generate wisely.